All right, well, I guess it's time, so let's start then. Hey, so yeah, is the sound okay? I can't hear myself, I guess. Okay, good. All right, so I didn't really have any idea for the subject, so I guess I'm just gonna do a bit about basic IPv4, then move on to IPv6 because that was one of the questions that people asked. Talk about routing, talk about how interconnections between networks work, and I guess we'll see if we have like how long that takes, and then look how that goes, I guess. Yeah, so let me just boop. There. All right. So well, yeah, in the beginning were computers, right? So originally in the 70s or 60s, I guess, you had like universities and like places like that that had big, not mainframe, but big mini computers. So like Unix computers that didn't actually require a full room and didn't do only one task at a time. They had multitasking computers, but they only worked locally originally. So at some point someone decided, hey, I want to be able to exchange information with other people, and so we need to connect two of these computers across multiple universities, because like who would need multiple computers in one university? That doesn't make sense. We need to connect between, I don't know, University of Idaho and MIT, I guess, because everything's at MIT. So we can communicate without using postage, and also probably work, like share the computing power. So when I'm not using my computer, I can lend it to them, or get the results of their computations or stuff like that. And so the idea was you would like lay a very long cable between the two, like this, and then connect the computers to the cables, and then you're done, right? Because like there's only two computers on the network, so it's easy. If you get a message on the cable, it has to be the other computer, so you don't need to identify them. You don't need you basically don't need any media control, because there's only two people on there, and there's a few like cables dedicated to sending, and a few cables dedicated to receiving for both. So you don't need to make sure nobody's like there's not multiple computers talking at the same time on the same wire. It's easy, right? So you just talk and it works. So basically it's like they're the same computer, they just have an interface between the two of them. And so that worked fine without any complications. But then at some point you ended up having to have like more than two universities connected. So let's say I add I don't know, UCLA. I have no idea if UCLA was part of the network at the time, but who cares? And so then you have three computers on the network, and then that's where the problem starts happening. So the problem with that is, since you can't have like a few physical wires dedicated to sending data and a few physical wires dedicated to receiving data anymore, because there's more than 2 computers, and so you would need like more, like you need to increase the size of the media as much as the computers, as much as you add computers to the network, right? So that's that's a pain. So you don't want to do that, because you need to upgrade the whole thing every time. And then you also can't assume that the person who's speaking is the one on the next side anymore, because, well, you know, there's more than one other side. So at that point, you need to identify who's talking, right? So the first thing you do is add Ethernet, because for now everyone's connected on the same network. So Ethernet is what we call a level 2 protocol that does basically access control. So it identifies who's speaking. So for example, this computer got a MAC address. So a MAC address is something that looks like that. Something like this, and then this one has another MAC address that's the same thing except .11 at the end, and this one has the same thing except it's 12 at the end. So now when you're talking, you have, instead of just sending the data, you can send a packet that is a formatted data unit. So yeah, so you have like the data you want, to put it at the end here, and then at the front you put a header, and the header contains the information that allows you to identify which computer is speaking, whether or not there's been any problem with the transmission and stuff like that. So in Ethernet, which is a very simple protocol, the header is comprised of the source address, the destination address, the CRC, which is a control code basically that checks that the packet hasn't been modified in transit, and that's basically it. All the other informations are useless basically. And so that way you can check who's sending the data and who it's sending it to. And then, for example, if the MIT is sending data to Idaho, UCLA receives it too, because this doesn't discriminate where to send the data. It just replicates it and sends it everywhere. And so UCLA receives the data, but it can see in the header that it's not actually the destination, and so it just ignores the packet basically. And in Ethernet parlance, the packet is called a frame, but that doesn't matter. It's still like the basic idea is a packet. So that's level 2 networks, and that works fine. You can add as many, well, basically as many other computers as you want on there, and it works pretty much fine, except except a few things. First, at some point you will have crosstalk, which is when multiple computers are talking at the same time. Well, since you don't have enough like independent channels to have them send their own data directly, then they're gonna talk on the same channel, and then basically you get noise at that point, because when you get multiple signals on the same channel, they interact with each other and none of them are readable anymore. So you need some way to control that nobody's talking on the network when you are talking. You need some way to like back off and then start talking again later. You need a way to make sure that the data hasn't been corrupted between the time it's left and the time it arrives, and the farther you are from the other computer, the most likely it is that you'll get some corruption. And the more computers there are on the network, the more it's possible that someone else is talking when you are. And so the way to do that is CDMA CD, right? Hang on. How to make sure about that? I don't remember. Great. Yeah. Right, that's it. And so that is a way for Ethernet to check, well, for computers to check that whether or not their data intersected with someone else's, and to resend them after a random interval of time. And so yeah, you have to add a few things on top of that, but that basically works as long as you're only building one network. But then at some point, someone, like some university, starts having two computers, right? Which is because some other department asks for one, or because they just didn't know what to do with the money they got from their students or whatever. And so at that point, they want to connect that other computer to the network too, but you know, they don't want, well, no one's just gonna, like, they're not gonna add a second link like that, because that is weird. You have two links going there and then one to each other university, and that makes it like more complicated. You have to identify another unit on the network and stuff like that. So so the way you do that is you connect your computer here, and then this one is connected here. So you cut that link, and then you have one computer connected to the other, and this one is connected to the outside network. Of course, I'm simplifying here. They the original university networks didn't use Ethernet per se. It used another level 2 protocol, and it doesn't really matter. The idea is the same, and it's a good way to explain Ethernet. And so so here you have another computer that has another MAC address, and that works not fine, actually, because the problem with that is the way you send in Ethernet is you send something with the source and the destination, right? I guess it's the other way around, but it doesn't really matter. And so when you do that, if you send a frame from this one to, well, on the only link you have, which is this one, and say, okay, so the destination is, for example, this computer here, UCLA, you're going to have a problem, which is that this the other computer at MIT is going to say, oh, well, that's not me, so I discard the frame, and then there's no one else to get it because it won't retransmit it, right? And so that's, that doesn't work great. So you need some way to have your packets transmit from here to here through that computer here. And so the way you do that is, well, you can just tell this computer here to act as if it were a hub, right? So take all the frames that come from everywhere on any interface it has, and then just retransmit it to on any other interface it has, right? And that kind of works. So for example, if it got a frame from here to here, it would get it there and then retransmit it here, and then everyone else on the network would get it, including the destination. But that quickly saturates the media, right? So after a point, if you have like 10 computers here and they're all retransmitting on the shared network through only one computer, then very soon you're going to have like lots of packets going everywhere, and then this one doesn't know about retransmission here, so this one has to keep it in its memory and then retransmit it later, and it's a pain. And the other problem you have is, as long as you're only doing networks like this and like this, it's fine. But the moment you do a connection like that, right, with a third link that does a loop, then you're fucked, because when this one transmits its packet to wherever, it will get here, which will retransmit it here, here, and here. And then computer number 4 will get it, and then retransmit it here, and that's it. And then computer 2 will get it and will retransmit it here, because it's not the destination, and then it will be retransmitted here, here, and here again. And then you have a broadcast storm, right? Which you don't want to get, because it will amplify and amplify and amplify, and then at some point, since the transmission is not instantaneous, then at some point you will like saturate your network and everything will go crashing down, right? And so the way you do that, the way you prevent that is, one, you don't do storms, you don't do loops, which is a fine solution unless someone finds an Ethernet connector on the wall and decides they must plug their computer there or their phone there, and then suddenly a loop. Wow. Unexpected. And so you can't really defend against that. You can only decide not to make loops when you have like only a few computers like this. And the other way to prevent that is to do use STP, which is the what's the STP again? Whatever. Great, thanks. Why can I remember the fucking names of the protocols? It's spanning tree protocol. So it's basically a protocol that does that shuts down ports on equipment that would otherwise retransmit packets, right? So if you have like an architecture like this, where you have 4 computers connected like this, right? So that's pretty simplistic, but you know, whatever. The moment someone connects these two, for example, if there's no STP running, then you have a loop. If there is STP running on like any of these or all of these, it will recalculate the shortest way to get from this one to this one and to this one and to this one. And so it will recalculate the shortest way on this, which is through here. It will recalculate the shortest way on this, which is through here, and it will recalculate the shortest way on this, which is, well, whatever, and then shut one of the links, right? So here all 3 links are equal, but in reality you have like some thing to differentiate them. So either this one is slower than this one, or this one is you declare it to be less interesting because there's, I don't know, some interference around there or whatever. Or if nothing else discriminates them, then it will just pick the one with the MAC address that's lower, basically. And so it shuts down the port, and then your loop is gone. So your network works again, which is better than broadcast storms. So that's the way to do it, and some networks have been built that way, like very, very large networks have been built that way in the 80s and the 90s. But at some point you can't just have everyone have MAC addresses, right? Because the problem with that is when you have to broadcast everything to everyone, at some point you saturate your external gateway. So if you have the university network here, and not the UN, the university network, and you're connected through one gateway, which is here. That's my network. And here I have like 10,000 computers. That are all single linked through the gateway. Well, at some point that link is going to saturate, right? And because you have to transmit every single packet that comes from here to here and like through here, and then every single packet that is on the university network you have to retransmit to all your computers here, which is a pain, and it saturates your network really fast. So And the problem with that is that there's no way to know where the packet is actually gonna go, because the MAC addresses are random. So you can't just say, oh yeah, that starts with like 10, it must be for this university, and so only send it there. The problem with that is they're random, so you can't actually know who is gonna need the packet. So you have to send it to everybody. So the solution to this is to like go one level higher, which is what we call level 3 networks. So this whole level 1, level 2, level 3, it's derived from the OSI model, which is a layered thing like this, which is layer 1, then 2, 3, 4, 5, 6, and 7. Layer 1 is physical, so it's like the actual electrons going in the wires. Level 2 is access, so it's like the thing that manages MAC addresses, like it's the media control layer. Level 3 is the layer at which IP works, so it's the network layer. It's the layer at which you can start routing packets. Level 4 is transmission, so it's like TCP. It's the layer at which you can start controlling how the data is interpreted and transmitted between computers. So you have sessions, you have multiple ports, you have stuff like that. Layer 5 and layer 6 are absolutely useless, and layer 7 is application. So it's the thing that actually presents the data to the user. And so, yeah, that is theoretical. It was made in universities, and actually there are protocols to follow each of the layers, but they're like basically never used. They were never used, and they're never used anymore. The TCP IP stack, which is not a real concept, but whatever, basically uses Ethernet here, IP here, TCP here, and whatever protocol you want here, like HTTP or whatever. And this is not a protocol, it's just transmission of bits, of like electrical signals rather. All right, and so yeah, you need to have some kind of addressing that you can decide where the packets are going to go when you send them and when you receive them. So instead of sending, like making the addresses random, you need to have some kind of hierarchical structure so that you can decide who has the address that starts with this and this number, and then who has the address that continues with this and this number, etc. And so for this, we created IP. Well, we created a bunch of different protocols, but IP is the one that actually worked and actually was adopted, which is pretty funny when you consider that back then it was considered amateurish and not suited to actual networks. But basically IP is this thing where you have an IP address, of course, because it's the point of the thing, which is 4 blocks of like 1 byte of information, right? So 1 byte numbers. So you have like whatever, 0 to 255, 0 to 255, 0 to 255, and 0 to 255. And once you choose one number in each of the categories, then you have an address, right? So for example, I can do like 10.2110, 210.42.3, and here I have an IPv4 address, right? So it's called IPv4 because, of course, there were 3 versions before it, and nobody cares about them because they were never put in production. But you know, it's v4 anyway. So that's the basic structure of an IPv4 address, of course, and the good thing about this is that you can actually divide it in blocks, right? So if, for example, I can say, okay, you know, MIT, you're gonna get every single address that starts with 8, right? And the way we express that nowadays, but not back then, but nowadays, is 8.0.0.0/8, right? It's called /8 because each of the blocks is 8 bits, and there's 8 bits which are fixed, right? So only the first block is fixed in this address. And so this network is 8.0.0.0/8. And so here they have, like, I don't know how many millions of addresses, right? And so now when I'm a computer that's a gateway, instead of going, oh, well, you know, I just have to transmit that packet to everyone, I can look at the first number and see it's 8 and then go, oh, right, yeah, 8 is MIT, so I'll just transmit on their link, and I only get packets that are for my network, right? And so at first they decided it was useless to actually divide this into small categories, and they decided, yeah, well, you know, we already have byte boundaries, so we're just gonna divide them into 3 categories, and then these three categories will start with certain numbers at the start, so it's classes. And we're not going to talk about that because it's bullshit, right? It's not used anymore. We have a thing called classless interdomain routing, CIDR, since I don't know, 1997 or something like that. So it's been a lot of time. So let's not dwell on classes. Classful networking is not a thing anymore. Or it shouldn't. So yeah, the way we do now is we divide it, as I said, by using a mask, which is this thing here. It can also be expressed as 8.0.0.0 mask 255.0.0.0, which is a negative mask, and then you can also express it as mask 0.255.255.255, which is a positive mask, and that's why we use the slash notation, because this is confusing because you don't know which notation you're using. Well, you can, because if it starts with a 0, then you know you're using the positive one, but you know it's a pain. And so, and also, like, going, oh yeah, it's 252, and you don't actually know what that means by looking at it. So, like, how many bits are free and stuff like that. So you just use the slash notation in modern computers. So that's how you divide the IPv4 address. And so the IPv4 address, like Ethernet, is a packet structure. The IPv4 data unit is a packet structure like Ethernet, but it's a bit more complicated. So you have first you have a few bits that are supposed to represent the version, but nobody uses them because, of course, there's only one version of IPv4, which is IPv4. And then you have the length of the header. So that's it's supposed to be used for variable length options at the end of the header, but nobody uses that anymore either. Then you have some kind of type of service field, which is supposed to be used to set the priority and tell people what's going to be after the header. And so Nobody used that either. Well, nowadays you start to see applications that use it, but it wasn't used for a while. And then you have a congestion notification header, which is to say, oh yeah, this packet is like very important, or not important at all, so you can tell the importance of the packet. And so of course some people use that, but nobody actually parses it, because otherwise every single application would say, oh yeah, my packets are the most important, of course. Then you have the length of the full packet with the data. That's the length of the header, that's the length of the packet. And then you have some ID here, which is a way, an identifier, which is a way to make it possible to reassemble packets that have been fragmented, so cut into pieces. Then you have a few flags that are used for like a variety of things, not actually used much. There's one that's do not fragment, which is used a bit, but that's it. And then you have the fragment offset, which is to say if this packet was fragmented, this part only starts from whatever offset is in this field, right? And then you have the time to live. So this is a counter that's decreased every time the packet goes through a router. And then you have the protocol field, which is a field that says what's after the packet. So you have a value for HTTP, for TCP, you have a value for UDP, you have a value for whatever you want to send afterwards. And then you have the checksum, which is a field that's used to check that there wasn't a corruption in transit. And then you have the most important part, which is the source and the destination. And then you have options that are optional, of course, if the length of the header was larger than the length of the header before the destination, basically. And so this is one IPv4 address is 32 bits, so 8 plus 8, 16 times 2, 32. And so this is 32 bits, and these are 32 bits too, basically. So the length of the full header is 100 and I want to say 128. No, 160, something like that. Anyway, so yeah, that's the IPv4 header, and it's pretty long compared to what we saw with Ethernet before. But it works, and then you can build networks which look like this, which is here's like one router. So routers are noted like this, and then behind that you have one network, and then they're interconnected to another router which has its own network, and which is also interconnected to another router which has its own network, right? And here you can actually build loops, right? Because on the router you tell this is like 10/8, this is 8/8, and this is 9/8. And so on this router you say okay, so to reach 8/8 you go through this link, and to reach 10/8 you go through this link, and to reach the rest of the internet of the IP space, the rest of the addresses, you go through whichever you want. So I don't know, this link, for example. That's what we call the default routes. So this one has a link to the internet, basically, is the idea. And they have the same thing. They have routes that tell them, okay, so 9 is that way, 10 is that way, and for this one, 8 is that way, and 9 is that way, basically. And so that's basic routing, right? The idea is when you get a packet for this network, you don't have to send it to this router anymore, which means that this link is not congested as much. And then you can actually make your network hierarchical, and so organize your network. And you can do the same thing in your organization. So in this network, you can actually make it so that you have like 9.1/16, so 9.1.0.0, and all the addresses that are after that is used for, I don't know, the math department, and then 10.0.0/16 is used for accounting and whatever. You can actually build your network as a hierarchical structure, and you have less problem with saturation of the links and stuff like that. And you don't have a problem with loops anymore, because if you do this, well, if you don't add a route here, because these computers have a route to basically a gateway here, which goes through here and then through like the main router here to go back there, right? And so if you add a link here, well, basically nothing happens, except if you add a route here to these computers there to tell them to go through that link to reach 9.10/16. Otherwise, it keeps working as usual. And if you do add a route there, well, it still keeps working, because they just start sending their traffic here, and then that's it, basically. There's no, they're not sending it to everyone on the network, and so it doesn't do a broadcast storm anymore. So that's how routing works, basically, originally. So that's the basic concept. And then once that started working, we started wanting to do more with that, and so at some point the internet happened a little bit, and so suddenly we had a large, very, very large network which interconnected all the other like small networks which had been assigned addresses, right? IPv4 addresses. And so you had this whole thing where, for example, Apple back then had a large network, and so they had their router on the internet, and then such and such university had their router, and General Electric had their router, and Ford had their router, and everyone wanted to have their own internet connection. And so like everyone had their own address block, and the address blocks were assigned depending on the size of the organization, and how friendly they were with the people who assigned them, basically. And so back then, lots of organizations that didn't necessarily need large blocks got very, very large blocks. And so Apple got a /8, and like Ford got a /8 too, and whatever, they got very, very large blocks, because they expected to at some point need to add a lot of computers internally. And since back then there wasn't any mechanism to use private addresses locally, they just went with that, basically. And so they had like internal computers with public addresses that just went all the way through their router, and then the other side's router, and then through to the other computer on the other side. And yeah, they also didn't expect the internet to start working internationally. They thought it would be a small thing to connect organizations that were actually like companies and industrial that had like industrial needs or research needs, basically. Like they didn't expect like consumers to get internet access, because like why would consumers get internet access? That makes no sense. And so yeah, for a time it worked like that. Every router was basically in a big LAN and like in a big local network like this. So they were all connected through Ethernet cables or whatever they had at the time. And that worked. And then at some point, someone started reselling their internet access to someone else, right? And so, for example, this network became an ISP, internet service provider. So they had another network under them, which had either had their own address. So I don't know, these guys might have a /16. So either this network had their own address, so I don't know, a /16 too, or they didn't, and they just rented them from the ISP, right? And so the way that worked is they routed the traffic for these guys the same way they would route the traffic for anyone else. But at that point, everyone had to add the route to this block to their routers, right? Which is not actually a sustainable way to do this, right? And so the way to do this actually is to have the routers announce to the other routers how they are going to what addresses they are running for, right? So for example, if I have like 12.1/16 here, I can write 12.1/16 here, and this is 30.4/16 again. Well, at the previous point, this router would know, okay, so through this link is 30.4/16, right? And then through this link is whatever this network is, and etc. But at this moment, you have to manually add the route for this network 12.1 here to this link because you don't have it automatically. And so there was a need for an automated way to announce which prefixes, which networks you were going to route for on your access, right? And so that's when BGP was invented. BGP is the Border Gateway Protocol, and so it's the protocol for the gateway that's at the border of your network, so the gateway that actually handles sending your traffic to the internet. And so that protocol just is used to announce which prefixes you have on your network, right? So you basically just go, okay, so hey ISP, I am 12.1/16. If you want to route stuff to 12.1/16, you can go through me, and that's it, right? And then the ISP goes, oh, hey, great, I am 30.4/16, so if you want to route things to there, you can go through me. And then also, since I'm your ISP, I'm also the default for you, so I can actually route for what is the default for, which is 0/0, right? Because that's 0, well, any number, and 0 bits that are fixed, so any network falls into this. And so this router adds the route to 30.4/16 and 0.0/0 on this link, and then that's it. And the ISP adds the route to 12.1/16 on this link, and then that's it. It works between the two of them. But then at some point, some other network is going to want to contact this one, and so this router has to announce that prefix too, right? And so the way to do this is to, well, just have it re-announce the route, right? So if these two establish a BGP connection, then this router is going to say, hey, I'm actually 30.4/16 and 12.1/16, but I'm not your ISP, I'm just like another network, so I'm not going to send you the default route. And this one is going to say, hey, I'm like, I don't know, 2/8, and then that's it, it works. So this network knows how to contact this one, and then this network knows how to contact this one, and since this one has a default through this one, then it knows how to contact this one anyway. Generally speaking, ISPs send the whole all of the routes they have to their customers, so they would actually send, hey, I have 2/8 now, but it's not like necessary, it works with the default route. And so now you have to establish BGP connections with everyone, right? And start sending your routes and start receiving their routes, and then when everyone's connected to at least a few networks that do have all the routes, right? Then that starts working. So in that context, if the whole network is comprised, if the whole if the whole network is connected to these four routers, then the internet works through these whole routers. We say they have a full table. They have a route table that contains every network that's out there, right? So they have the full table of routes, and so that works. We also call that the default free zone. So it's the place where they don't have default route. And so that works. That works until you realize that there's no authentication, right? And so, and by design, there's no authentication, because if there were, the ISP's router couldn't announce the customer's address anymore, of course. So you need to have no authentication on this protocol, or at least you need to have no. You need to have, like, if you want to have an authentication, you need to have an authentication that can forward through another device that you don't trust. And so the problem with that is that if suddenly this router starts announcing 2/8, it's actually like 3/8, but if it starts announcing 2/8, either because it's a malicious action, it wants to get the traffic for this one, or it just someone made a typo and typed 2 instead of 3 or whatever, well, everyone's going to start routing there, right? Because the problem with BGP also, well, with IP in general, is that you don't have a good way to prioritize routes. So if I get a route to 2/8 and a route to 2/8 here, I don't have a way to know which link is the fastest and which link is the slowest, and I don't have a way to tell whether it should go there or there, basically. So generally, routers will start routing half and half, right? Round robin. So it will start sending half the traffic to this side and half the traffic to this side. And but I guess it depends on the implementation you have. You can also have implementations that just choose one of the two routes, delete the other, and then just send all the traffic to one of the two. And the problem is that it's random. There's no way to prefer one of the sides to the other. The only way to make sure your route is preferred to the other one is to have a smaller mask. So if I have 2.0/16, 2.0/9 and 2.128/9, this is equivalent to 2/8, right? Because you have from 2.0 to 2.127 here, and from 2.128 to 2.255 here. So that's equivalent to this. Since these are /9s, they are more they have priority over the /8, right? The idea is that you can always if I subdivide my network, I need to be able to say, okay, actually I was assigned 12.1/16, and I want to announce 12.1/16 to every single small network here, but then this small network, we need to contact this small network, and it's faster to go that way. So you can announce smaller routes and have the network not route through the larger one. So smaller routes always take the priority. And so that's one way to defeat the non-authentication of BGP, right? So you can just say, I'm just going to announce the smallest routes I have, and then nobody will be able to hijack me except by also announcing all the smallest routes possible. And then, yeah, I won't have a way to prevent that. But, you know, sometimes you have problems and you try to fix them, and you look at how you could authenticate connections, and you look at how you could authenticate routes, and you look at all these complicated problems of distributed trust and stuff like that. And sometimes you just, you know, give up, right? And that's what they did. They just went, well, you know, we're gonna be fine. You know, we don't need authentication. We're just gonna rely on everyone being honest and trustworthy, which is a great plan when you have a big network that's composed of the whole world. And so that's how the internet works, basically. That's how networks interconnect. So they start sending their routes to BGP, and then the other side accepts them, and that's it. There's no authentication. There's nothing on top of that. Nowadays, it's evolved a little bit. So there's still no widespread. We're starting to see widespread adoption of authentication on routes, like 40 years after IPv4 came out. But it's still not like really widespread. There's only a small number of networks that require them. A lot of them accept them, but not a lot of them require them. And then we also have the most basic safety feature of the world, which is, oh yeah, actually I'm just gonna accept these network sizes from you. So if I'm ISP-A and I'm connected to ISP-B, I can just accept all their routes, and that's fine. You know, the internet works like that. But I can also say, well, you know, I need security, and to add security to this, I'll say, okay, you know what, I'm just gonna accept like about 100 routes from you, like about 100, and because I know, you know, you have like, I don't know, 80 networks, so you won't grow to like 200 immediately. You will grow through to 90 and then 95, and then when I'll see your network starting to go to 95, then I'll increase that number. But for now, I'll only accept 100 routes from you. And then also to prevent you from sending me like a whole /8 or even the whole default, I'll start only accepting like /16s from you, right? I won't accept any route that's smaller, larger or smaller than a /16, right? So if you send me a /8, I will just deny it. And that's basically what security on the internet is: a number of routes and a size of route, and that's it. And so if network B starts to stop announcing their own prefix and send me all of Google's prefixes cut up into /16, then of course I'll accept them, as long as there's not more than 100. Then, you know, that's how security works, right? You just accept stuff. And so that's how it worked for a long time. Now there's other mechanism that I will talk about in a future episode, in a future stream, I guess. So that's interconnections between networks, right, on the internet. And so that's the technical side. But then there's the social side, right? Because let's say I'm an ISP, right? I'm ISP A, and you know I'm a small ISP, right? I wasn't born, I wasn't actually a thing when the internet started, and they assigned /8 to everyone, and when everyone was in a large LAN. So, you know, I have A/16. It's like, I don't know, 4.5/16, and I have a few clients, of course, and I have a few upstreams, right? I have a few other networks from whom I buy internet access, and that I pay to have internet access, actually. So, of course, I pay them. Like they won't just give me internet access out of the goodness of their hearts, right? I have to pay them. And my clients, of course, pay me as well, because I'm not giving them internet access out of the goodness of my heart, right? And so that's the basic solution, and I buy what we call transit from these ISPs, right? And these ISPs are bigger than me, and they have more connections, and so yeah, they can give me actually internet access to the whole internet, and that's why I buy transit from them. And they might buy transit from someone else, or they might just be connected to everyone, which works too. But I don't really know, and I don't really care, because they just give me internet access and I pay them, and that's it. But the thing I can do is, well, some other network just contacted me, and that's ISPD, right? And they told me, well, you know, I think you should buy internet from me, actually. I also have transits, right? And I also pay them, and I also have customers which pay me. But I'm not really larger than you are, but you know, I can give you a good price, and I think you should buy internet from me, right? And so you look at their offer, and it's actually not really more interesting than what you have here. But what you could do, since you're about the same size, is just connect to them like this, and none of you pay the other one, right? You don't actually route the whole internet for the other one. What you do is you route your own prefixes for the other one. So they are 3.4/16, and so instead of like going through, for example, if I want to contact them, instead of going through my ISP, which goes through the internet, which then goes through their ISP, which then goes through to them, I just use the link we just built, right? Which is better for everyone, because I don't have to pay my ISP for the traffic, and they don't have to pay their ISP for the traffic. And so for me, it's better because I don't have to pay. For them, it's better because they don't have to pay. And the only price is building a link between us, right? Which is pretty easy, actually. You just build a link and then establish a BGP session, and you start sending each other your route, right? And so that's what we call peering, right? You connect with your peer, with another network that's approximately the same size, right? And so now we can have a hierarchical structure to the internet, which is you have the really big ISPs at the top that only have clients or peers, right? So if I only have clients or peers, then I never buy transit, right? I only sell transit or just peer with other networks, right? And so that's what we call tier 1 ISPs. So a few of them are like Orange in France, well, in Europe, I guess. And I think Verizon is a tier 1 too, for example. And I don't know, there's others like NTT in Japan, or well, in the world generally, but in Japan. Cogent is supposed to be a tier 1, but you know, who knows. So the problem with tier 1s is, the problem they have and the problem people have with them is that, let's say you are a network, right? And you go to a tier 1, you tell them, well, I'd like to peer with you because, I want to have access to your network through without going through a transit, and I can give you access to my network without going through a transit, well, through one of your peers, which is better for everyone because you don't have to pay and I don't have to pay. And they go, well, actually, I don't have to pay right now because my peerings, like, to get to your network, I'd only go through a peering, and you go through a transit, so you have to pay, and I get a share of that, and so I don't have any incentive to peer with you because I don't gain anything and you do gain something. So why would I help you for free out of the goodness of my heart, right? And so the other thing is, if you want to peer with them, if you want to have access to their network without paying your transit, the other way they could do that is by selling you their transit, right? So you could become one of their customers. So they don't have any incentive to have you as a peer. They have actually counter incentives, because they could get you as a customer and then, of course, get money from you. And so they don't want to peer with people, but they have to because, of course, they're all big enough that if they stop peering with each other, they wouldn't have access to the whole internet. And they have to defend the client contract they have with like large networks. So Verizon could have a client contract with OVH, let's say, right? I don't think they do, but whatever. OVH is a large network, right? And so Verizon has to defend the contract they have with them, because if they go to peer with Orange, then suddenly Orange gets the upper hand in the relationship they have with Verizon, and so they run the risk of not being a tier 1 anymore, because they could actually have to become a client of Orange to have access to their previous customers, right? And so the problem with that is that the peering arrangements are secret, of course, because if you start telling people how much your clients pay you and who you peer with and who you buy traffic from, it becomes hard to tell people you're tier 1, and then it becomes harder to peer with other tier 1s, and then you run the risk of becoming a tier 2, which is networks that have more than one upstream and who are large but not large enough to be to only have transits. And so there's a whole thing of politics. That's why I said Cogent is rumored to be a tier, well, says they are tier 1, but is rumored to actually not be a tier 1 and have by transit. And you can see the routes taken by some packets, right? You can see which routes are announced to whom and stuff like that, but you can't actually tell who's paying who. And that's the problem, because you can have a free peering arrangement and you can have a paid peering arrangement. So with Orange, generally, if you have a free peering arrangement with them, you are a tier 1. If you have a paid peering arrangement with them, then you're probably a tier 2, and so you pay them for only their network. And so they are present on some. They can also do some free peering with some small networks, but then they only send a fraction of their routes, right? And then you have the tier 3, which is networks that only have one upstream, right? And so these are just I don't know. If I had a BGP connection in my living room, I would be a tier 3, right? I would only be buying internet from one upstream, right? So that's the limitation of networks on the internet, right? And you have these small number of tier 1s who are sharing the world basically, and then you have tier 2s which are large enough ISPs or networks, and then you have tier 3s, which are consumer networks, I guess. So yeah, that's the internet. Now to see about routing in more detail, I guess. Great. So if anyone has questions, just go ahead, right? All right, no questions, no questions. Oh yeah, go ahead. I mean, I expected people to go about questions as we go, so. Well, as I said, v4 is for, because yeah, there were 1, 2, and 3. 1 was internal to ARPA, which is the U.S. defense organization that developed IP with universities, and 2 and 3 were development tests, and then 4 was the one that was actually released to the public. And 5 is similarly, 5 was a development test and was never actually released and used, and then 6 became the future protocol that has been the future for the last 20 or 25 years, I guess. All right. So, all right, let's talk about NAT. So v4, pretty quickly, it became pretty quickly clear that there wouldn't be enough IPv4 addresses to give a unique one to everyone, right? Because, well, the general public started using the internet with public ISPs, and more and more organizations started being on the internet. Newspapers, like stores, shit like that. And so there were more people than expected, and then it started becoming not a US only thing. It started becoming international. First in Canada, and then Mexico, and then across the ocean, and then all over the world, I guess. And so it became, as I said, pretty clear that there wouldn't be enough IPv4 addresses as far back as like 1995, which is pretty early by the internet's history. Oh yeah, as I said, if you have any questions about any of the things that I said, just go ahead on the chat. I'll answer them as I go. So yeah, they started thinking that they couldn't give everyone an address. Well, they started thinking they couldn't give every device an address, and then they thought, we might just give an address to every customer. And so consumer ISPs specifically started not getting enough addresses for all the customers, right? Because a /16 is like 65,000 addresses, and so once you run out of that, you have to either ask another block, or just get a /8, which you can't do anymore because oops, we're out of /8s, right? And so the addresses, by the way, are were distributed by a US organization, which is ARIN, I want to say. Was it ARIN at the first originally? I want to say it was ARIN originally, and then it was oh no, it wasn't ARIN originally, it was something else. All right, well, at some point so yeah, originally you had like one organization in the US that just went, oh yeah, well, you know, you want an IPv4 block, okay, you get this IPv4 block, that's it. And so they just like actually assign however they wanted. So, and then, so at some point, European and other countries, like governments, started complaining that they were like they needed a local authority on who gets which blocks and stuff like that, and so they started dismantling the organization that was there previously, like IANA, I want to say, ICANN, oh, one of these. And so the US got ARIN, right, which is the American Registry for Internet Numbers, right? And so the Europe got RIPE, which is, or RIP, which is the Réseau IP Européen, which is a French name because the French were a pain about that. And Africa got Afrinic. And Asia Pacific got APNIC, right? It's true. And so these are the organizations that give you IPv4 addresses depending on where you are. And so, yeah, if you are an ISP and you only have a small block because all the big blocks are gone, then you are starting to look at only giving one address to each of your customers instead of one for their first computer and one for their TV and one for their second computer and one for whatever the hell they want. And so what you do at this point is think, well, you know, I have a router on their premises, right? It's their gateway. So that's my router. Then I have a bunch of customers here, and each of them has a router, and then behind that they have like their own network, their home, their computers, their TVs, their whatever. And so the thing I can do, and that's inside the home, right? It's their box or their modem router or whatever. And so what I can do is load some special software on this thing that does network translation, address translation, right? Network address translation, NAT, N-A-T. So NAT does a thing where every single device in there actually doesn't have a public address. It has a private address that is like in one of the private blocks. There are 3 private blocks. It's 10/8, 172.16/12, and 192.168. Wow. /16, right? And so generally they use the third one because the 2 previous ones are more used for other things. And so what you do is you actually put a local address here, 192.168.1 /24 generally even, and then here you put the public address, right? And so every device here has a private address in that network, right? And so, for example, the computer might be 0.2, the TV might be 0.3, and whatever the hell other stuff you have here might be all the other numbers. And so the problem with that is that by design, IP needs interconnectivity from one side to the other. Because if you remember, here you have the source and the destination in the packet. And so if my computer is here and doesn't know that I'm translating the address, it will put 192.168.whatever.2/24, well, not /24, but 0.2 in the source, and then put, I don't know, whatever address they want to reach, like twitch.tv, the address of twitch.tv in the destination, right? And so the packet will go through every single router in the route and then arrive at the Twitch servers, and then Twitch will look at the packet, well, the server will look at the packet and go, well, okay, it's destined to me, that's fine, but the source is 192.168.whatever, and so I can't send it back because I don't know where it goes, right? It's a private network, and so I don't actually know which where it comes from, basically. So it doesn't know how to respond. And that's not great, because generally speaking, when you contact a server, you want to respond from that server. And so the way to do this is to add special software on the consumer equipment, on the router there, and tell it, okay, when you get a packet from the inside network, from here, from the private network, that's going outside. If it's going inside, you just route it normally. If it's going outside, then you take the packet, you slice it up, and you remove the source address and you replace it with your public address, right? Your public source address. And then you assign it a source port. So NAT only works with TCP and UDP and a few specific protocols like that. So it needs special handling for these protocols, and so it uses the source ports to identify where the packet's coming from. So when you reach Twitch, you want to go to HTTPS, for example, so you go to port 443, right? That is the destination port, and it's fixed, of course, because you want Twitch, well, the server, to know what service you're actually requesting. But on the source port side, it doesn't really matter, because the server is going to reply on the same port, but you don't specifically have any service on that port. You're just using a random port on there. And so NAT uses the source port of the request and assigns, has a table inside the router that says, okay, so that request was on port 10495, and so that's the request that goes from the computer to Twitch on port 443, actually. And so then it sends that packet with the public address to Twitch, which now knows how to respond because it has a public address as the source, right? And then so it does whatever it has to do, responds that, and when it arrives to the router again as the response, the router looks at the NAT table and goes, oh yeah, actually that packet is destination. The destination port is 10495. I know what connection that is. It's the computer to Twitch to port 443 connection. So I'll just forward it to the computer, replacing the destination address from the public address that was in the packet that I received with the local address of the destination. So yeah, the computer only gets the packet if it's destined to it. So if you leave the public address there, it won't actually read the packet. You need to replace it with 192.168.whatever.2. and then the computer gets the reply, and then they can exchange like that basically. And every single time a packet goes inside and outside, there's a lookup in the table and or a write in the table to make a new entry. And so yeah, NAT works like that. The problem with that is that you have to, well, one problem with that is that you don't actually have end-to-end connections anymore, right? So if I want to host a server in my home, well, you know, it becomes hard because because basically I don't actually have access to my ports, right? And so if I put a server here, well, I have to tell the router that actually everything that goes to port 80 or 443 or whatever I want to use should be forwarded only to this server and only on this port, and then you know, the other way around again. And so an ICMP, for example, which is another transmission, well, kind of a transmission protocol, has to be also forwarded here and stuff like that. And so yeah, it breaks the end-to-end concept of the internet as it was designed. And then the other problem is that every single time you get a packet, you have to disassemble it, change the destination address, well, change the source address or the destination address depending on which side of the, well, where it's going and where it's coming from, and also change, like, recalculate the checksum, and you know, do a bunch of stuff like that. And that's a lot of, well, it's not a lot of computing power by today's standard, but it's a lot of computing power by consumer routers standard. And so yeah, it kills it eats a lot of CPU for consumer servers. And then the other problem is that you only have 65,000 ports for TCP, and the same for UDP. And so, well, depending on how many connections you have at the same time, you can only have, well, you can basically only have 65,000 connections at a time, which isn't well, it can be a lot for a consumer, but it's not a lot for like servers and stuff like that. And so it's not great. So basically, you're selling your consumers reduced internet as it is. And then at some point, people figured out that actually, even with that, we won't have enough IPv4 addresses, and so we need to start slicing them smaller again. And so instead of doing NAT with a full address, they give you 1/4 of an address. So you have they cut the port range into 4, and so someone gets like 1 to 15,000 or something, and then the next person gets 15,000 to 30,000 or something, and then same thing again and again. And so that's one customer, one customer, one customer, one customer, and that works fine with that, except you can only have like 15 or 17,000 connections at a time, of course. But the problem with that is that with NAT like this, with an IP, a public IP for every customer, but a public IP for every customer, you could have a server at your home, right? It's a pain, but it can work because you can do port forwarding. And so tell the router, if I have a packet on port 80 and it must go to the server on port 80, right? You can do that. But with this kind of NAT, you can't do that anymore because you only have like 0 to 15,000. And so if you're in that range, then of course you have the HTTP port, you have the SMTP port, you have all the important ports that are basically 1 to 1024, right? But if you're in that range, then you don't have them, right? It's not routed to you anymore, and so you can't actually do port forwarding to your server, so you can't host a server anymore. And then the other thing some ISPs do is they have the internet there, and they have their router here, and then they have the customer's router here, and they do a first layer of NAT here, and then a second layer of NAT here, which means that of course they use even less, like fewer IPs, right? Fewer public IPs, because they only have a public IP here, and then they have a private one here and a private one here, and then a bunch of private ones here. And that works, but the problem is that it breaks the premise of the internet even worse. So as long as you don't actually need end-to-end connections, that works fine, because of course it's not at the first time here and a second time here, but then when it comes back, this router will change we'll do a lookup in its NAT table and then send it back here, which will do a lookup in the NAT table and then send back to the actual machine. So it works, but it's awful design, which is a thing, and then it's a waste of a lot of computing power, and then of course it breaks everything that actually needs direct connections. So that was NAT. That's the hack that's been used since about 1998 to keep more IPv4 addresses, like to use IPv4 addresses more efficiently, I guess. You could put it that way. And then the other solution to IPv4 exhaustion is IPv6, right, which is a whole other protocol. So yeah, in 1997, 1998, the IETF, which is the Internet Engineering Task Force, a group of internet operators that decide how the protocols work and stuff like that. So the IETF decided to remark that there was going to be IPv4 exhaustion and that they wouldn't have enough addresses, and that soon the whole world was going to use IP, and that stuff like that. And so they said, okay, we need a new protocol, right? We need to extend the IP addresses space. And so back then there were two routes that were considered. The first one was, well, we could just take IPv4 and just, like, I don't know, use two times as much space for the source and 2 times as much space for the address, the destination, and that's it, right? The addresses become twice as big, and so the space is not just twice as big, because it's of course it's powers of 2, so it becomes, like, I don't know, very much larger, right? And that could have been the choice, but then by then they had other ideas, because IPv4 was also not actually a great protocol for what the internet was at the time. There was a bunch of stuff that didn't work that well, and as I said, BGP was a pain, because the routing table was becoming too large, basically. And so adding more numbers to, like, basically enlarging the addresses would not have helped that much. And also you would still need routers that know how to manage that, and so that would still mean replacing every single device on the network, or upgrading them, or whatever. And so it's a huge pain. So you don't want to do that. If you're gonna do it, you want to get an actual benefit from it, right? So might as well add features to the protocol and change the way it works, and make a new protocol. And so they designed IPv6. which was to be the protocol of the future, right? It had lots of new features. It had larger addresses, of course. It was simplified compared to IPv4. So instead of having that whole thing with like length of the header, options, flags, and stuff like that, it had a header that looks like this, right? So you have version, once again, which is useless, but you know, that's just how we do it. We can't have a protocol without a version in it. Then traffic class, which is the same as basically the same as the type of service here. So it's a thing that says, okay, this traffic is actually more important than others. You know, some people just won't let the idea of prioritizing based on declaration go, even though everyone knows it doesn't work in the real world. Then you have the flow label, which is a thing that says in IPv4 to decide what was a flow. So a flow is a set of packets that are the same connection, basically. So if I download a movie, I want all the packets to go from the same source address and protocol and port, and go to the same destination address and port, right? And stay on the same path as much as possible, because if it changes path, then it can have like more lag or less lag, or something that changes the way the connection works. And so I don't actually want that. I just want the traffic to follow one path and work the same way. So to decide what is a flow in v4, since there isn't a flow indicator in the v4 prefix, in the v4 header, you do a thing where you take what we call a 5-tuple, right? So it's source address, destination address, source port, destination port, and protocol. And this is the 5-tuple that allows you to identify a connection, right? Which is weird, because the destination port is generally the same as the protocol, since most protocols run on a dedicated port. But you know, whatever, that's how it works. And so they decided, you know, that's actually a pain. We don't want to have to calculate a 5-tuple every time. We're just gonna put a flow label, and you just set whatever you want there, a number or whatever, and every single packet that has the same flow label in it will actually be the same flow, and that's it. Which is a good idea, I guess, generally. That's pretty good. And then you have the length, once again. That's only length of the payloads of the data. The length of the header isn't included. And then there's next header, so it's basically the same thing as protocol in the previous one. So it says, oh yeah, the next one is TCP, basically. Then you have hop limit, which is TTL, but it has a different name because, you know, why not? And then you have a pretty much larger source address fields, and then a larger destination address field too. And that's it. There's no option, there's no variable length, it's fixed. It's a lot easier for routers to process, because there's no need to look at the length and then decide if there's options at the end, then go through the whole thing, look at the options, and then go back and, you know, recalculate the checksum and stuff like that. You just process that much data, which is what, 300 something? Yeah, 300 and something bits, 320 bits, and then you know that you've gone through the whole header, and that's it. And there's no fragmentation either, as you can see. At least there's no fragmentation in transit. So in IPv4, a router can just decide, oh well, actually, you know, I'm a router here. I have this connection here and this connection here. Actually, this connection has like per packet on this connection I can send like 1,500 bits, right? But on this side I can only send 600, right? And that doesn't work, because if I receive a packet that's 1,500 bits from that side, I have to retransmit it on this side, and I can't because it's bigger than the limit here. So what I'm going to do is take that packet that I received, cut it up into bits, and then I have more smaller packets that I can send over that connection, right? And so that's called fragmentation. And so what you do if you fragment the packet in IPv4 is you say, oh, actually, you copy the header and basically you take the payload and cut it up into pieces. That's you don't care about the payload, but you take the header, copy it to the next new packet, and then set the fragmentation offset to a certain value, right? Which is the size of the previous packet plus the header, minus the header, and then when it arrives on the other side, it looks at the fragmentation offset and then reassembles the packet and reads the data. And then you also have fragmentation on the source, right? So if I want to send 9,000 bits from my computer, and I know my link is only 1,500, well, I'm gonna have to cut my data into multiple packets, and then I can just fragment it, and that's fine. And then I'll send it fragmented to the router, which can fragment it again if it needs to, but it doesn't have to, right? But it can. And in IPv6, there's no fragmentation in transit. There's only fragmentation at the source. And since the fragmentation is at the source and you have the flow label, you can just say, well, actually, that's the same flow, and that's it, right? And so it's basically a lot simpler than IPv4 was, that the IPv4 header was. Yeah, that's exactly it. You have a /8. You have one IP from the /8, and it's a public IP, and it's just, you don't have NAT. It just connects to the internet directly. And so, yeah, that's how the internet used to work, and that's how IPv6 works too. And so, yeah, IPv6 addresses are a lot longer. They're 128 bits. When IPv4 was 32 bits, so that lets you do the calculus. It's like 4 times larger. And so, of course, masks work the same way, except instead of writing like 0.00000000120 or divided by 8, I guess, a lot of times, like 8 times. I don't know how to count. Whatever. A lot of times you just write the / notation only. That's the only notation that works in IPv6. And addresses aren't written the same way because they would be very long to write in the 1 byte per byte format. So instead of doing that, you just take 2 bytes in hexadecimal form and write that basically, and separate that with colons. So a hex value is 2 bytes, right? Right, it's 2 bytes. And so the way you write the address is hey, actually I'm you know, I don't know, fd colon 01 colon 53 colon whatever colon 1, right? And that's only 2 per unit, but you can actually write f colon 0000 if you want to write it completely. If you want to write the top one completely, that would be 00fd 0001 0053 blah 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 0001, right? And then since we don't want to write a whole bunch of zeros, you can actually shorten that whole, if that whole thing is just 0000 colon 000, etc., you can just shorten that into fd colon 01 colon 53 colon, and that means this here is filled with zeros, colon 01, or just 1 actually, I guess. And so yeah, IPv6 addresses are longer and they have a more complicated way of being written, but they're not that complicated either, I guess. So for example, my IPv6 address here is here 2001 470 10 1F07 BF8 23E0 4474 E797 1789. That's a long address, right? And oh yeah, oh no, you will be able to DDoS me. And so yeah, that's a long address, and people have argued that it's hard to remember, but you know, that's just what you get when you need longer addresses, I guess. That's just life. And so yeah, that's IPv6 works basically the same as IPv4 in all respects. It routes the same. It's the same basic concept, right? But the differences are that, for example, there are a few differences in how the addresses are handed out and how routing works and stuff like that. So first of all, you can't actually assign a customer a single address, right? In IPv4, you take a customer or a small network and just give it a /32, which is one address, right? And in v6, the smallest allocation you can do is /64. That's not a technical limitation; it's a, like, I guess, political limitation. So the AETF says, oh no, yeah, we don't want to replicate the problems we have with NAT in v4, so you just hand a /64 to everyone, and a /64 is like how many trillions of addresses, and so yeah, that it will be enough for every customer, I guess. So that's how you fix the NAT problem, right? And then you have other stuff, like for example, in v4 there's no way to assign addresses to machines per se, right? In the IPv4 specification, there's no single way to assign an address automatically to a machine. You have to do it by hand. And so later they developed DHCP, which is a protocol that allows a network administrator to automatically assign addresses to the machines in one network. So you have a network like that, And so you have a DHCP server on that network that sends nothing basically originally. And so when a new machine connects to the network, it wants an address, so it sends a DHCP request to everyone, and then the DHCP server responds with, oh yeah, right, you can just get that address actually. And then the machine like assigns itself that address, and then it starts working normally, right? And so that's a hack on IPv4. There's no actual way to do that in IPv4. DHCP is not part of IPv4. It's another protocol. In IPv6, they wanted to have a mechanism to do that inside the protocol because, well, you know, if we were making this thing, might as well fix the problems we have with it, right? And so they did this. Unfortunately, they did this in two ways. Because that's the problem with v6. It's not that it's necessarily complicated, it's that there's multiple ways to do everything, right? And so for address assignment, there's the thing that's called SLAAC, S-L-A-A-C, which is basically you connect your computer to the network, and it will request the prefix of the network through on broadcast. So it will send everyone, hey, actually, what network am I connected to, basically? And someone or everyone will answer saying, hey, actually, you know, the network is whatever / whatever, and then the computer will go, oh, okay, fine, then I'll assign myself this address. And so it will just decide, okay, this is my address now, and if nobody objects to that, then it's its address, right? And you know, that works, but the problem is that you can't control who's going to get which address. And also DHCP also sends DNS settings, gateway settings, stuff like that. And so there's a bunch of ways in SLAAC to have one server which will be the central setting point that will tell the computer, oh, actually, you know, yes, this is the prefix we use, but also you should use this gateway, and you should use this DNS server, and you should use this time server and stuff like that. The problem with that is that these are extensions, and not everyone supports them. And well, nowadays mostly everyone supports them except Android, but historically not everyone supported them, and then so you have a bunch of problems that network administrators can't control, basically. And also they can control which device will have which address, which is a problem when you want to control your network, right? When you want this machine to have a fixed address, for example, you have to set it on the machine and not on the network, which means that you can't be sure they will be respected at all times and stuff like that. And so there's also DHCP v6, which is a hack of DHCP to make it work on IPv6, and it works basically the exact same way as DHCP, except it has some more settings, right? And so, for example, in DHCP v6, you have since there are so many addresses, instead of just sending one IP to the machine that connected, you can actually do a thing which is called prefix delegation, PD. And so the DHCP v6 server will tell the machine that just connected, oh, actually, you can just, you know, take that whole prefix, it's fine. And then it will also you just tell it, well, you know, you're fine with that, just take it. And prefix delegation works in a specific way where the client, there's a way to authenticate the client so that it always gets the same prefix. And that's done with a specific magic number that the client knows and that the IPv6 server knows, and that is linked to the prefix in question in the IPv6 server's configuration. And there's a bunch of weird extensions to the IPv6 which make it complicated for no real reason. Like, it could have worked exactly the same way as the IPv4, but they decided to add some specific extensions, basically. And yeah, so it's more complicated than DHCP is, and that using IPv4 would be, but that's not a specific failure of IPv6. It is a failure of Slack and of DHCPv6, basically. And yeah, that makes it more complicated to use, but it's not due to IPv6 specifically. The good part of IPv6 is that, well, one, you don't need NAT anymore, of course, which is a pretty good thing. And the other thing is that for network operators, their routing table becomes a lot cleaner. So in IPv4, you had a lot of people who just disaggregated their prefixes. So if you're assigned a /20, for example, you can just keep it as /20 and start announcing a /20 to people, like to your ISPs and stuff like that. Or you can take it and then cut it into pieces and make, like, I don't know, 2 /21s or 3 or 4 /22s or 8 /23s or 16 /24s, right? And the problem with that is that, well, you can go smaller, but on the internet generally you can't announce anything smaller than a /24. And so a lot of small networks will take their networks and just cut them all down to /24s, because since they don't have a very large network and don't want to do transit, well, don't want to have all their physical sites interconnected, they just take the network and just assign a bit there, a bit there, a bit there. And so the routing table for everyone becomes larger and larger. Everyone that has a full table, as I said before, just suddenly has a very, very large routing table for no good reason. And so in IPv6, the smallest unit you can announce publicly is a /48, and the smallest unit you can assign to someone is a /64. And most people publicly get at least a /48, generally a /52, right? Or a /56. Generally a /44 or something like that. And then, they cut it up into /52 or /56, but they can't announce that, right? Generally, well, when you're a big ISP, you get a /32 or something like that, which is very large. But they can't announce their smaller prefixes, right? They can only announce their /48, and they mostly don't have a problem with that because it's easy to get more prefixes from the authorities that assign them, and it's cheap to get more, so you might as well just get more and announce the large ones. And so that fixes to some degree the size of the routing table, even though of course eventually there will be more /48 prefixes than there are /24s in IPv4, because there just are more possible prefixes than in v6 and v4. But even then, it's still easier to aggregate your network into larger pieces, because you have between /48 and whatever prefix you were assigned to aggregate them, basically. And the other thing with v6 is that authorities just give out larger prefixes to everyone, because there's no limitations on, well, there's a lot more addresses and a lot more prefixes, and there's no limitations on the size that you can get, basically. So if you ask today for a /32 as an individual, you might probably get it. And some people have argued that that's a big problem, because just giving everyone like n trillion addresses means that soon we won't have any more, and we'll have the same problem as with IPv4. But it's not actually a thing. One, because there are so many addresses in IPv6 that it's hard to comprehend. There's more. I think the number that was given is that there's more addresses in IPv6 that there are grains of sand on the Earth. So we're probably fine for a few years. And then the other thing is that we're only using a /3 right now. So like every single address that was ever assigned in IPv6 is part of 1/3. So if you do the calculation, there's 8/3s, of course. So if at some point we start seeing that, oh no, we are running out of addresses and do that /3, we have 7 times as many addresses to burn through before we have to replace with like IPv whatever the next one is. So we are probably going to be fine for a few years. But yeah. And so the way IPv6 address and network and route and stuff like that assignment work is more complicated than in IPv4, and you have a thing called RA, router advertisement, which allow you as a router to tell everyone on the network that you are a router and that you have a route for a default route or a route to whatever. And the problem with that is it's very badly implemented on a lot of operating systems. Like the protocol itself works fine. And for example, on OpenBSD, you have a lot of control over the way the protocol works. You can debug when you received an RA, from whom, what it contained, stuff like that. But on Linux, for example, there's no debugging that, and there's the whole configuration is done through sysctls, and basically it means that any computer on the network can just send an RA to the network, and everyone just accepts it passively, and suddenly everyone's got a different route than they did before, which is not great. And you have no means of debugging that, when in DHCP you did actually. You had to make a request to get a route and then, or an address or whatever, and then you could see who answered and stuff like that. But here you can't anymore, and so that's a pain. But yeah, interconnection between different networks still work using BGP, but instead of using IPv4, they use IPv6, and so that's it. It's the exact same protocol. It just uses larger addresses, and BGP can be used for much more than just v4. It's also used for Ethernet and stuff like that. But here on 4v6, it just uses v6, and then that's it. And so the other thing with BGP is that you have another number used for identification. So as I said, you have like network A, network B, and network C. These two peer. This one is a transit. And so the way this works in BGP is that once again, this network C advertises its routes, and network B re-advertises them, and then network B would probably advertise the default route to network C, and then that's it. And the way you advertise it, actually, you don't just say, oh hey, I have this route. You say, hey, I am this number, this ID number, and I have this route. And so the ID number is called an ASN for autonomous system number. An autonomous system is a network that's self-contained, so it can route internally. It has multiple machines, and it routes internally. And so once you have an ASN, you connect with the next, with your peer or your transit or whoever, and you tell them, okay, hey, I'm AS number whatever, and I have this route, right? And that's one. It allows the routers to have prefix lists. So yeah, lists of prefixes that you are allowed to send. And also it allows them to have a discrimination on the AS number that you use. So if you're ASN 4 and I'm ASN I'm AS 2, I can in my router configuration I can say, oh, okay, so any advertisement that comes from AS2 you decline, of course, because that's me, so I'm not gonna accept someone else advertising my own prefixes to me. That's probably a bug or an error on their part. And any advertisement that comes from ASN number 4, AS number 4, you only accept like 10 of them, because I only have like, I don't know, 5 prefixes, so you only accept 10 prefixes from them. And you can also say, on this link you only accept these ASNs and stuff like that. And so yeah, that's how you identify people on BGP. The other use of ASNs is that in the modern BGP security protocols, among which BGP-SEC and RPKI ROA. So BGP-SEC and RPKI ROA. So BGP-SEC is BGP security. RPKI is routing public key infrastructure, and ROA is route origin authorization. And so BGP-SEC uses cryptography to identify, cryptography between two routers, two ASNs, to identify who is advertising who, basically. And RPKI is as the name says, a public key infrastructure. So the organization that assigns you the IP address that you use has a private key, or has a key for you, a key pair for you. And so for ARIN, for example, you have to generate it yourself and then upload the public key to ARIN, and then everyone is fetching that from there, and then you sign your advertisements with the private key. For RIPE, they handle it for you, because it's I mean, they're already the organization that gives you your IPs, so it doesn't really matter whether or not they have your private key for advertising these IPs. It doesn't change anything. But you know, ARIN does shit like that. And so basically, yeah, you have a key pair, you publish the public key, you sign your advertisements, and when someone reads them, well, they can check that it was you that made the the advertisement basically. And so yeah, the advantage of that method is that, for example, let's say I'm network C, I assign my advertisement of my prefix to network B. Network B can go and check out on the organization, so Arin or Ripe or whoever, get my public key from there, and then look at the assignment, the advertisement I sent, and check that the signature on that advertisement is made using the right key. And if that matches, then they can accept the advertisement. If it doesn't, they can reject it. And the interesting part is that, because that's easy, right? But the interesting part is that when they advertise my prefix, right, they advertise it with the signature I send them. Hang on, no, that's not right. They sign it with their own key, and I personally told to my authority, the number authority, that I allow network B to re-advertise my advertisements, my prefixes, and so they sign it with their own key, and then network A can check that the signature that was made with network B's key, which is authorized to advertise that prefix, and then they know that it's an actual real and authorized advertisements, and then they can filter out all the non-authorized advertisements that come from other people, either maliciously or by error. And so, for example, in this setting, Pakistan Telecom cannot announce YouTube, which happened a few years ago. And that's being deployed more and more. NTT, for example, uses it a lot. And I don't know, nowadays most internet exchange points, IXPs, which is places where you peer with people, most of them enforce it nowadays. And so yeah, that's the nowadays we have some level of security on internet advertisements. All right, I guess I'm done for this stream. I'll just take like questions and then go and have something to eat because it's 3 p.m. Yeah, sure. Hang on a sec. So, yeah, when I was learning. Well, I went to a kind of French university system and learned about networks there, I guess, a bit. But most of what I learned was from this book, which is basically the same information as I learned at university. So, might as well buy the book. It's shorter. And it's that's the French edition, but it's Networks by Tannenbaum, and it's really good. They have everything from they basically go through network layer by layer. So you have one physical layer, two like layer 2 MAC address layer. They talk about MAC in detail here, and then they go through network layer and IPv4, IPv6, BGP, but basically everything, anycast, multicast, stuff like that. So that's like, that talks about everything in networks in general. If you want more information on like network politics, internetwork politics, the way BGP works in the real world, and how transits and peerings are established, and how networks do their political discussions and stuff like that, there's a really good book called The Peering Manual, which is it explains how peering works, how it's less expensive than transit, of course, and how to establish peerings with big networks, even when you're a small network, and how the politics actually work between networks. And apart from that, I'm half convinced that there's a lot of information about systems networks. So how networks are implemented in Linux, how networks are implemented in BSDs, and stuff like that in how's he called? Michael Lucas's book generally have good information on networks. His OpenBSD book is pretty good. Well, his OpenBSD book is really good. His FreeBSD book is pretty good, and they both have good information about the way the networking stack is implemented and how they work on these operating systems. And there's also, if you want to just have a quick overview of networks as a network for system administrator. A quick overview of networks for a system administrator, for stuff like that. I think he wrote a book. Yeah, he wrote Networking for System Administrators, which is a pretty good book too, which explains the basics of how internal networks and local networks work, and how the internet works as from a systems administrator's point of view, basically. Great. Well, thanks, I guess. I might do like others on other stuff, more specific stuff, and yeah, sure. And yeah, I'll put it either on YouTube or some PureTube instance, or both, I guess. No, that book is by Tannenbaum, which is a US author, so you can get it in English. I just have the French edition here. Yeah, I said YouTube or PeerTube or both or whatever. I guess I just have to find an instance that works for that. So yeah. If that's it, then I guess alright, well, if that's it, then I guess goodbye, and I'll do another one of these someday, I guess. Thanks for being there, and see ya. I hope that was useful. Bye-bye.